Hey, students, good to see you all here waiting for me. Floria, Anna Jung, Ding Jojo, and Ruby. I can see you. I'm going to move straight to the presentation for today. We are going to have a class for just maybe like 30 minutes, and then you have to do some exercises, okay? Since we only have 40 minutes to be here. All right. I'll now share my screen. Is there a question about last time's work? Does anybody have a question about what we did last time? I remember last time we talked about, what did we talk about last time again? We had talked about motion due to gravity and weight. Does anybody have a question? Maybe a problem you couldn't solve? I need to hear confirmation. Since I cannot see any of you guys. I cannot be talking to myself here. Is there a question about last time's work?
No.
No.
Okay. So today we are moving on. Essentially, most of what we are doing is the same, or the same reasoning. We'll be talking about normal contact force here, and the motion of objects in the vertical plane. This force, the normal contact force, in some books, this force here would also be referred to as normal reaction. We didn't study Newton's third law yet. We are going to study it in a chapter later, but I have introduced Newton's third law to you guys. The normal contact force, or the normal reaction, is a reaction force. So, in a previous lecture, I have told you guys about when any two objects are in contact. Let's say you push on the wall. That is you. You push on this wall because you are in contact with the wall. Then it means that you are applying a force on the wall. That is your push force. And I told you guys that the wall will also push back on you. The wall will push back on you. And if this wall is not moving, or you are not moving, the force that the wall pushes back on you will have the same magnitude as the force that you applied to the wall. That is a brief summary of the normal contact force. And this force, the normal reaction, because this force only exists because of this one. If this force is not there, then this one will not be there, right? So this force will be a normal reaction. Why normal? It is normal because it always acts at 90 degrees to the surfaces in contact. Mm? Let's look at the normal contact force for an object that is lying on a horizontal surface. Let us consider a table here. And let's say on this table is, there is a book on the table. The book is lying on the table at rest. Now, why is it at rest? We know that normally there is a weight force acting on this book, the weight of the book. But the book is not moving down and it's not moving up. It means that there must be another force acting on this book in the opposite direction to cancel the weight, right? That force is the normal reaction. It is at 90 degrees to the surfaces in contact. And since this book is not accelerating up or not accelerating down, it means that the normal reaction is equal to the weight, right? So the magnitude of the normal reaction will be the same as the magnitude of the weight. A lot of times, students think that anything that is lying on a horizontal surface, the normal reaction is equal to the weight. That is not always the case. Let's say that this book is lying on this surface and then you push on this book also. You go ahead and apply another force on this book. If you push on the book downwards, let's say you push with a force of 10 newtons, for example, then you did not change the weight of the book, right? The weight remains as it is. But again, as you are pushing, the book is not accelerating down. There is no acceleration. It means that the forces are again balanced. So when forces are balanced, it means the sum of forces in the downward direction should be equal to the sum of forces upward. So in this case, weight plus your 10 newtons should be equal to normal reaction. So if you push on this book, the normal reaction force will increase so as to balance up with the forces acting downwards. Let's say instead of pushing on the book now, you try to pick up this book. You try to lift up the book with a certain force. Let's say you apply a force of 5 newtons upwards. But the book does not lift up. It stays down. You apply this force, but the book still stays at its position. In this case, we still use Newton's second law. The sum of forces upward should be equal to sum of forces downward. So 5 plus normal reaction should be equal to weight. That will give you normal reaction to be weight minus the force that you try to lift up the book with. So you guys should understand how to analyze these situations. Next case is what is that case? There should be another case here. The next case I will look at is when the when the table is at an angle. I'll call this normal reaction on an inclined plane. So in this case, you still have this table. You have the book, but then you try to lift up this table from one angle. So you are going to have something like this. Your table now is an inclined plane, inclined at an angle theta. Let's say this book is still lying on this table. Let's assume that this book is not sliding down yet. You lift the table edge up a little bit so that the book is not sliding down yet. It is still at rest. Again, we need to find all the forces on this book. I think in the first worksheet I gave you guys a question like this, right? There was a worksheet with a question like this. And I asked you to draw the forces acting on this object. I saw one student try to draw the weight and drew the weight like this. Which student was that? I think that was, I will not call the name. But weight is always acting vertically downwards, okay? Weight is always vertically downwards, no matter the situation. So your weight will be vertically downwards. Then the normal reaction is always acting at 90 degrees to the surface. The normal reaction, this angle must be 90 degrees. Is this all the forces acting on this object? On the book, is there another force? Anna? I didn't hear from you.
No.
No other force. Is there another force, Floria? This book is not sliding down.
Friction.
We haven't talked about friction yet, but there is a frictional force on the book acting upwards to keep the book at rest. If there is no friction, then the book is going to slide down, right? When you tilt it a little bit. Okay, Anna? There is a frictional force acting upwards. Okay? But we are focusing on normal contact force today, so we're not yet talking about friction. Now, we will talk about the elevator problem again. We have seen the elevator problem before. We will talk about it again. Remember, those of you who are going to the UK to study, in the UK, you will often see lift, not elevator. They will often say a lift, motion in a lift. So, let's say you have an elevator or a lift. Let's just draw a box for an elevator or a lift. Of course, an elevator should have an elevator cable, right? And then there is a motor here, which pulls this cable up or releases the cable for the elevator to go down, right? Let's say there are some people, you are in this elevator. You are standing in the elevator. Let's say your mass is m, and the mass of this whole thing here, the mass of this whole box is big M. What are the forces acting on this elevator? We will first consider the elevator as a whole. This is the same as just, this is the elevator, and then that is the cable, and this is you and the elevator with total mass M plus M, right? And so, what forces are acting here in this situation? I need you guys to name some forces that are acting. Ruby, one force.
Gravity.
Gravity. Use the proper word. Use another word.
Weight.
Which direction is weight acting? That's
downward.
Weight is acting vertically downwards. What is the magnitude of the weight? What is the magnitude of the weight of the whole system? Still Ruby. What? What? What is the size of the weight, please? The weight of this whole system is the weight, mass of you plus the mass of the box times G, right? Is the mass of the whole system, which is your mass plus the mass of the elevator times G, right? Which other force is acting in this case? Lynn?
Tension.
Where is tension acting?
At the top of the box.
Yeah, there is a tension here, vertically upwards, right?
Yes.
So here there is a tension on the string. Very good. So that tension, let's call it T. Now, what I'm trying to illustrate is this. If, let's say this lift is taking you up to the 25th floor where I live, it's moving up. So let's say it's accelerating upwards with acceleration A. So we will use Newton's second law, summation F equal MA, right? So since our acceleration is upwards, we will take the force upward minus the force downward. So because this force will become negative, we take upward direction as positive. So the sum of forces, T, this force becomes negative. So we'll have T minus M plus M times G should be M plus M times A times the acceleration of the box of the system, right? Now, this is a very interesting equation we got here. It's a very interesting equation, and we'll talk a little bit about this. Now, if in this case we said if the lift is accelerating upwards, we said it's moving upwards and is increasing speed, you have this equation. This equation also holds if the lift is moving upwards and is decelerating. What did I say? No, if it is moving downwards and is decelerating, then acceleration is upwards, right? So all you need to think about is direction of acceleration, not direction of motion. If it is moving downwards and is slowing down, that is taking you from the 25th floor down to the first floor. When it is arriving the first floor, it starts to slow down. When it is slowing down, the acceleration is upwards. This equation still holds. All right. Now, let's take the case in which the lift is now, maybe the lift is moving upwards and is slowing down. If it is slowing down, then your acceleration is downwards, right? Or it is moving down and is speeding up. It takes you from the 25th floor and starts to go down. When it is starting to go down, it will accelerate and then move at constant velocity and then slow down. So we are taking the first case in which it is accelerating downwards. It starts to move down, is accelerating. In this case, this equation becomes this force minus that force, right? Because when you sum your F, it's always a good idea to take direction of acceleration to be the positive quantity here. So sum of forces, that's the force in the direction of acceleration minus the force in the opposite direction should be equal to mass times acceleration. So you have M plus M G minus T is equal to M plus M A. But I would like to make a note here. This equation and this one, there is no difference. If you used this equation in this second case, it is also valid. However, your acceleration will be negative because it's in the negative direction, right? Now, when we use it like this, acceleration becomes positive. So we can say that for this second case, we have taken our downward direction as positive direction and the upward direction becomes negative. I hope that is not confusing for you guys. Is it confusing for anybody? No. My idea ultimately for you guys is always when you use Newton's second law, when you use Newton's second law, you should take the forces, the sum of forces in the direction of acceleration minus the sum of forces in the opposite direction equal mass times the acceleration. In other words, I always try to my best to take direction of acceleration as positive instead of direction of motion. Now, the last case, if this lift now is moving with constant velocity, you know, when the lift takes you from the 25th floor, it will first accelerate and then move at constant velocity and then decelerate, right? Let's say it's moving at constant velocity, whether upwards or downwards. In other words, acceleration is 0. In that case, you look at either of these two equations, you'll see that the tension is equal to m plus m times g. So if it's constant velocity, this force should be equal to the tension. So you know how to analyze that. I think we have talked about this a while back in some classes before. And this is here, I'm just giving more details about it. That's not going to be all we are going to talk about the lift. This lift problem is a very interesting one. It's a very interesting one that is often talked about, and you have, most often there is a question about this in the examination. So I wanted to spend a little more time on it. We have 10 minutes left, but I must finish with this lift problem. In the second case with the lift, we are not now looking at the lift as a whole, but we are looking at you inside the lift. You are standing inside the lift now. What are the forces acting on you? There is your weight, vertically downwards, mg, and there is the reaction, the lift on you, call that R. All right? Now, let's say the lift is accelerating upwards. It is essentially going to be the same thing. Let's say the lift is accelerating upwards. We still use Newton's second law, summation F equal ma. So in this case, we are going to have R minus mg for u should be ma for u. From here, you can calculate your normal reaction. So R will be mg plus ma, which is mg plus a. If the lift is accelerating upward, that is the value of the normal reaction. I usually do not like to go to calculating R because in problems that you will be given in the exam, you will be asked to look for maybe the acceleration and the normal reaction. So you have to think about this equation and then also think about the whole lift. They usually twist the problem a little bit. Now, if the lift is accelerating downwards, the equation becomes mg minus r equal ma, right? And if the lift is moving at constant velocity, before we look at that, I want to look at these two cases first. So this gives us r equal m into g minus a. So now you guys can see in the problem I gave you guys before, I did ask you, the questions were, the lift is accelerating upwards. State whether the normal reaction is bigger than or smaller than mg. For this first case, if the lift is accelerating upward, you can see here that r is bigger than mg, right? R is bigger than mg, is bigger than your weight. And for this second case, if the lift is accelerating downward, you can see that r is smaller than your weight. And now the third case, if the lift is moving at constant velocity, this means acceleration is 0, then you use any of these equations, a is 0, you'll get r equal mg, all right? And these questions usually will ask you, if you are standing on a bathroom scale, something that will measure your weight. The scale that you are standing on will measure the value of r, okay? So if the lift will be accelerating upward, you will see that the scale will read a bigger value than your normal weight. If the lift is accelerating downwards, the scale will read a smaller value than what you normally weigh. But if the lift is moving at constant velocity or is at rest, the scale will read the correct value, okay? Okay, let's end the meeting and then restart, okay? We'll come back and then solve some problems. Just, you guys should sign back in with the same code. Thank you. Okay. Right, otherwise. Share screen. Okay. For a few minutes, let's look at 2 problems here that I took from your book. The first problem says that an elevator is carrying a man of mass 70 kilograms. So mass is 70. It's accelerating at constant acceleration from rest to 10 meters per second in 2 seconds. So we interpret the problem. The elevator is carrying the man, and the elevator is accelerating upward with a constant acceleration A. The mass of the man is 70 kilograms. So we are asked to find the size of the contact force on the man. We are asked to find R on the man. There is going to be a weight mg or 70g. 700 newtons. 70g is 700 newtons. So it's accelerating upward with acceleration that we're asked to find R. We know that R minus 700 should be 70A. That gives us R equal 70A plus 700. But we do not know A. So we have to find A from what the problem gives us. We are told that it accelerates from rest. U is 0. It goes to V10, and the time T is 2. We are looking for acceleration A. Which equation should we use here? V equal U plus AT. U is 0, so that's 0. So we have 10 should be equal to 2A, giving us A equal 5. So this means that the normal reaction will be 7T times 5 plus 700. Okay, this gives us a typical problem in which we can practice how to solve the elevator problem. Second problem, a weightlifter is trying to lift a bar with mass 200 kilograms from the floor. So we have the floor, and there is a bar on this floor. The weightlifter is trying to lift it from the floor. The mass of the bar is 200 kilograms, so the weight of the bar will be 2,000 newtons. He lifts with a force of 1,800 newtons. So he applies a force 1,800 newtons. But he cannot lift it off the floor. It doesn't move off the floor. It means this bar is still on the floor, so there is still a normal contact force. And we are asked to find the value of this contact force. We are asked to find the magnitude of the contact force. So if we use Newton's second law here, the sum of forces downwards must be equal to sum of forces upwards because there's no acceleration. So R plus 1,800 should be 2,000. giving us R equal 200 newtons. So the normal reaction will be 200 newtons. Okay, for today, you guys should watch the videos in lesson 5. There are a couple of videos in lesson 5. Watch them, and your homework is also in that lesson. In lesson 5, you'll see it there. Okay, there are like 2 or 3 videos there with examples. Okay, thank you. See you guys.